About 3,800 years ago, in an Egyptian settlement on the banks of the Nile, in a place we now call Lahun, a scribe was writing numbers onto a sheet of papyrus. Perhaps he thought it was just an ordinary calculation. But the few lines he wrote would leave behind a much greater question for mathematical historians thousands of years later. How did the ancient Egyptians calculate fractions? And more importantly, why did they break fractions apart in exactly the way they did? In 1889, the British archaeologist Flinders Petrie uncovered a large collection of papyrus fragments during his excavations at Lahun. These were not treasures from a royal tomb. There were letters, administrative records, medical texts, veterinary texts, and mathematical documents. They were the remains of the everyday life of an Egyptian settlement. And among these fragments was a tiny mathematical text. Today, we know it as Kahun Papyrus, Section 4, Fragment 2. Its catalog number is UC32159. At first glance, what we see looks simple. 2/3, 2/5, 2/7, 2/9, and so on. But here we encounter one of the most important features of ancient Egyptian mathematics. Egyptian scribes generally did not write fractions in the way we write them today. They expressed fractions as sums of unit fractions, fractions whose numerator is 1. For example, 2/5 was written as 1/3 plus 1/15. Because if you add 1/3 and 1/15, you get 5/15 plus 1/15. That is 6/15. And 6/15 is equal to 2/5. Mathematically, the result is correct. But now, the real question begins. Why? Because 2/5 can be represented in other ways as well. There can be more than one way to decompose a fraction into unit fractions. So the question is no longer, how did they calculate 2/5? The real question is, why did they choose 1/3 plus 1/15? Why this decomposition and not another one? Perhaps the first explanation that comes to mind is physical measurement. They were measuring grain. They were distributing bread. They were producing beer. They were giving rations to workers. But this immediately creates another problem. If the purpose was simply to measure a physical quantity, why would they need a compound fraction such as 2/5? Why not express the quantity directly using unit fractions? Perhaps the 2/n table was not primarily a table of physical measurements. Perhaps it was a calculation table, a tool for converting the result of a division such as 2 divided by 5 into the fraction language used by Egyptian scribes. But now an even bigger question appears. If the scribes could calculate the result of 2 divided by 5, why did they write these results down in advance? The small Kahun fragment contains this kind of decomposition for odd denominators. About 200 years later, the Rhind mathematical papyrus contains a much larger version of the same table. It begins with 3, then 5, 7, 9, and continues all the way to 101. 50 different values of 2/n. And now we reach the truly remarkable point. When the 10 surviving values from 3 to 21 in the Kahun papyrus are placed beside their counterparts in the Rhind papyrus, the results are identical, not approximately, exactly. Scribes living in different periods used exactly the same decompositions. Now, to understand Ahmes's calculations, we first need to learn the notation system he used, because when we look at these pages through modern eyes, we only see disconnected numbers. Yet, for Ahmes, these numbers were operational instructions. In Ahmes's notation, the single mark over the numbers 3 and 15 means 1/3 and 1/15, respectively. The 2 dots over the number 3, on the other hand, mean 2/3. In other words, these small marks essentially serve the same function as the fraction bar we use today. First, Ahmes considers dividing the number 5 by a certain number, so that the result is less than 2. To achieve this, he chooses the value 3, which is close to the number he obtains by multiplying 5 by 2/3, meaning he reasons that dividing 5 by 3 will yield a result less than 2. Furthermore, in the second line, he confirms this statement by writing the 3 and the adjacent 3 with a dot over it as 3 plus 1/3. Then, Ahmes divides the number 5 by 3, and by showing the result in the third line as a 1 alongside a 3. With 2 dots over it, he actually demonstrates that this value is 1 plus 2/3. Considering which part he needs to obtain the number 2 inches, the numerator, Ahmes decides that this missing part is 1/3 and draws a line next to it. Next, Ahmes asks himself what value he should multiply the number 5 by to obtain 1/3, determining this value to be 1/15. He then marks this 1/15 as seen in the fourth line, establishing the final result as 1/3 plus 1/15. Confusing, isn't it? Let's take a look at this operation with our own interpretation to understand what Ahmes was actually trying to do. Ahmes was actually breaking down the numerator of the fraction in his head according to the value of the denominator. In other words, could he actually have been thinking of the value 2 as 1 plus 2/3 plus 1/3 divided by 5 and performing the operation accordingly, because otherwise it would have been difficult for him to come up with the value of 1/15, right? Now, let's examine the method Ahmes used for 2 divided by 7. We can say that Ahmes didn't start by multiplying by 2/3, as he did in the 2 divided by 5 example, because he first divided the number 7 by 2 and found the result to be 3 plus 1/2, meaning 3.5, realizing that this number was not less than 2. He then divided the number 7 by 4. Anyway, let's verify the solution. As you can see on the screen, the result comes out absolutely correct. Wait a minute. Ahmes performed another operation on the right side. He found it using the doubling method. Interesting, isn't it? What do you think this is? Don't forget to write your thoughts in the comments. Now, let's examine how he divided the number 9 by 2. We see that the scribe once again multiplied the number in the denominator by 2/3. This means that perhaps he started this way again for the subsequent numbers. However, the value 7 comes to mind. We see that he did not multiply the value 7 by 2/3 when finding 2 divided by 7. This shows that this is not a constantly used method. The scribe successfully handled the task here as well, breaking it down into unit fractions. What if the number was larger? For example, how would it play out if we were finding the value of 2 divided by 29? Let's take a quick look at the value. Ahmes chose to divide the denominator by. Ahmes selects the number 24. But why? Couldn't he have chosen another number? On what basis did he determine this? Let's examine whether the 2/3 value would work here. If we multiply the number 29 by 2/3, it gives approximately 19.3. Could it be that Ahmes was using this value for numbers that are multiples of 3? The answer is yes. Making the most of the legacy he inherited from the Kahun Papyrus, we see that Ahmes actually used the 2/3 value for numbers that are multiples of 3 inches, all 2 divided by and divisions, all the way up to the number 101. However, we also notice that in the Kahun Papyrus, the 2/3 multiplier was used for the number 11 as well. Now, let's verify the calculation for 29, as shown on the screen, and bam! We were able to obtain the result just like Ahmes did. But our investigation does not end with mathematics. If we want to understand what Ahmes was actually doing, we also have to look at history.
Why was this table created? Was it for a school?
For scribal training, for the everyday work of the Egyptian administration, for grain and bread distribution, or was it a general calculation, tradition, shared by all of these activities? There is another important question. Why 101? Why does he divide the number 101 by 101? When finding the result of 2 divided by 101, the Kahun table reaches 21. The Rhind table reaches 101. Why exactly 101? Why not 99? Why not 103?
We do not know the definitive answer. Perhaps 101 was sufficient for practical calculations. Perhaps it was the boundary of an older table. Perhaps it was a standard used in scribal education. Or perhaps Ahmes was simply copying an earlier mathematical tradition. We cannot yet know for certain.
And in the end, we are left with something remarkable. A small mathematical fragment from Kahun, a much larger table in the Rhind Papyrus, 2 different periods, 2 different scribes, but the same mathematical results. At the very least, this tells us something important. These decompositions were not random, but we still do not know exactly how they were produced. Perhaps the Egyptians had an algorithm. Perhaps they used divisors. Perhaps they used common multiples. Perhaps they combined several methods. Or perhaps the results had become standardized through generations of mathematical training. And now our task is to test these possibilities one by one. Because we do not have only a 3,800-year-old piece of papyrus. We have 50 mathematical traces, and perhaps, by following those traces, we can reconstruct how an ancient Egyptian scribe actually thought at his writing desk. And speaking of how these scribes thought, if the mathematical puzzle connecting the Kahun and Rhind papyri blew your mind, you have to see what else Ahmes was hiding. To discover how these very same fractions were used to shatter one of the biggest optical and historical myths, you absolutely have to watch my previous documentary, The 100-Year Lie, The Eye of Horus Illusion. You can click the video on the screen right now to keep unraveling the secrets of the scribes. Also, if you want to support my vision of building a massive library dedicated to the history of mathematics, make sure to hit that subscribe button. Follow the limit. Go beyond it. Stay with the limit and beyond. Stay with mathematics.